So what we're going to have a look at in this tutorial is how we apply materials to a part. And one of the things that allows us to do is to get the system to tell us the mass of the part. So the way that it does this is the material that we apply has a density for that material associated with it, and the system can then combine that with the calculated volume that the part takes up, and from those two values it can obviously then calculate the mass of the part. So we're going to look at how we apply materials in SolidWorks. We're then going to have a look at how we get SolidWorks to report on what the mass of the part is, so that the user can see that information and can make decisions based on it. And then the final part of this tutorial, we're going to use that ability to monitor the mass of a part, and we're going to get the system to change our design slightly, or optimize our design, in order that we can hit an actual figure for the mass. So initially the part that we're seeing on the screen here will be too heavy, and we will allow the system to optimize the size of a certain feature on the part, so to shrink that feature down, and its goal that we will give it is that it should hit a certain window of mass that we want it to end up as. So the first thing that we're going to do, we'll just have a little look at this part. This is a form of moulded part. It has some rib features on the underside. You can see these, 1, 2, 3. And the thing ultimately that we're going to let the system optimize about the design of this part is the thickness of these ribs. So when we get the current mass value, we will see that it's too heavy. We will then want to reduce the mass in some way. One way that we could do that would be reducing the thickness of the ribs, or possibly the number of ribs. We could do it in other ways as well, but this is the way that we're going to look at in this particular tutorial. And then the system will run a series of experiments, adjusting the ribs during each experiment, and it will pick the experiment that most closely hits our mass figure, or our mass goal that we give the software to hit. So the first step that we're going to do here is we're going to apply a real world material to our part, and the way that you do that in a part in SolidWorks is, the first thing, the part must be made up of a solid body. So this would not work if the part was purely surface bodies. Because as we've covered previously, surface bodies have zero thickness, therefore they cannot occupy any volume. So the system is unable to use a volume figure in the calculation to calculate the mass. So luckily in this part we do have a single solid body. So here it is in the solid bodies folder, and in order to apply a material to this solid body, and therefore the entire part in this case, we just right click there, go down to material, and go into edit material. And for this particular part we're going to apply an ABS plastic to the part itself. So you can see I've already selected that. If we wanted any of these other materials, there's quite a large library of various materials within SolidWorks. So there's quite a large library, particularly of metals. So you can see I'm browsing inside all the metals here. And in order to calculate mass of a material, as I've already said, the only real figure that we need in here is the density. So as long as a material that we select has a density figure associated with it, then we can calculate the mass of our part using that particular material. So as I've already said, we're going to apply an ABS material. Now I've set a very particular color scheme on this part, and I don't want to lose that. So I'm just going to set an extra option in here, or deselect an option, and that is in the Appearance tab. and I'm going to say do not apply the appearance of ABS. So if I'd left that checked, my part would then resemble transparent ABS plastic, and I don't want that in this instance. So you won't always have to deselect that, but in this instance, because I've taken the time to set up this kind of colour scheme and this sort of appearance on my part, I don't want to lose that. So that's why I've unticked that option there. So then I'll tick apply. I'll get a warning in this case about the appearance of the part. I'm going to click on no there. I don't need any of the options that it was offering me on that particular pop-up. Then I can close the part, and then if I want to check that that material has actually been applied to this part, I can browse inside the solid body that I applied it to, and I can see the material that's been applied there. So a material's been applied, so this part has a given density figure. So now we can calculate the mass of the part, or we can get the system to calculate the mass of the part for us. So I'm in the Evaluate tab here, and if you can't see the Evaluate tab on your systems, then you'll have to click on one of the other tabs, or rather you'll have to right click on one of the other tabs, go down to tabs, and just find the Evaluate option here and make sure you have a tick at the side of it, and then you should be able to see the Evaluate tab. The Evaluate tab has many useful tools within it, and it's used to evaluate certain properties of your design. So you can measure things like distances and areas and lengths of edges. The one that we're going to use in this case is the Mass Properties tool. So yeah, it's a very useful tab for various different ways of analysing your design or of evaluating your design. So I'm going to click on Mass Properties. The window that comes up is quite detailed. It has a lot of extra information, not just the mass figure of your part, so it might be worth just kind of familiarising yourself with other values that you can get within this tool. It will return the volume of the part for you, the outside surface area of the part, where the centre of mass or centre of gravity as it's sometimes known is of the part. So there's lots of different quantities that can be obtained within this Mass Properties tool, but the one that we're interested in is this one. What is the mass of the part currently? So it's currently set at, or it's currently being evaluated at 90.28 grams. And let's say for our design we have been given a mass to try and hit, so a mass figure to try and hit of 82 grams. So our part is clearly too heavy at the moment. So we're on 90.28, we want to hit 82. And normally, or almost always, when you're given a figure to hit, either a dimensional figure or a mass figure in this case, you will be given a tolerance. So it is impossible to hit an exact figure, or to be sure that you have hit an exact figure. So you'll be given a tolerance, which is essentially a window of masses in our case that it would be acceptable for the part to be. So let's say ours is 82 plus or minus 0.2 grams. So that gives us a 0.4 window of values that are acceptable. So we know what the mass currently is. So what we could do now, if we wanted to do this job manually, is we could go into the rib features and we could start editing the thicknesses of the ribs. So maybe we could reduce these down to 2 and then do a rebuild and then reevaluate what the mass is now. And as we can see now, we've gone too low, so then we would go back in and adjust it slightly and reevaluate the mass. Now that is a way of working that would probably eventually lead to the correct mass figure for the part, but it takes a lot of user input. It's very labour intensive in terms of a method of actually achieving your goal. There is an automated tool within SolidWorks which will do that job for us. So that's what we're going to have a look at next. So we're going to use something called Design Study to help us analyze and then optimize the design of this part to hit our mass figure. And the way that you access Design Studies is in the Simulation tab. So again, if you can't see the Simulation tab on your systems, the easiest way to activate it is to click on SolidWorks Add-ins and then just click where it says SolidWorks Simulation, and then it will load for a few seconds and then the tab should appear. So I'm going to go into that tab and I'm just going to click on New Study to get into the menu that gives me the option of which sort of study I want to begin, and I've already said in this case it's going to be a design study, and then I'll tick OK. So the setup of these design studies is split into three broad areas, and we will work through them from the top to the bottom. So variables is essentially any area of your design, normally a dimension, although not always, that you're going to allow the system to play with in order to hit your goal. So in our case, I already said that we're going to allow the system to vary the thickness of the ribs in our design. Now, we're using a single variable here so that our design study calculates as quickly as possible. But you can put multiple variables in your design studies, so you can allow the system to experiment or play with multiple dimensions within your design in order to hit a certain goal or a certain endpoint. So let's add some variables now. So I'm going to click on the drop down list. I don't currently have any variables defined, so I'm going to say add a parameter. Then I get into the parameters table here, and it's empty currently, but this first row has been highlighted. So what I'm going to do here is I'm going to select a dimension from my design, and you can see a lot of those dimensions have now become visible. So these are clickable values now. And I've already said the one that we're going to focus on is the width of the ribs. So I previously changed that from 5 to 4, so you can see that it's now set at 4 and it's showing around the rib feature there. So I'm going to click on that variable. It gets collected into the current row in my table, and then we always name these variables, because it is very easy, especially if you're entering multiple variables into a design table or a design study, to quickly lose track of which variable is controlling which element in your design. So I think we'll give it a kind of logical name. Rib width seems relatively logical, and then you need to press enter to accept that row of the design table. And then if we were going to add another variable, we would select the next row down, and then we would pick something else that we're going to allow the system to change in pursuit of our end goal. In this case, we're only using that single variable, so we can exit this design table, we can accept it. So I'll click on OK. Then the first entry in our variables table that we were just looking at gets entered here. Now if we put multiple entries into that table, only the first row would be entered into the actual optimization window here, so we would have to manually then add the other rows in. So we know that the current value that this is set at is 4. We also know that the current value is too high. So when we think about the range of values that we're going to allow the system to work within, it would not be helpful to allow the system to make that value bigger. So remember, it is currently 4. So the logic here is that the rib width is currently set to 4 millimeters, and the mass of the part is currently too high. So if that rib width was to increase above 4, say to 6 millimeters, the part would still be too heavy. The mass would be too high. So I'm going to reduce this figure down to what it is currently. So I don't want to let the system go any further above 4 millimeters for the width. How low do I want this to go? So in a sense, we're kind of having to do a little bit of estimation here to kind of set the range that we're going to allow the system to work in. 2 millimeters is a relatively thin rib, especially considering how thick the outer wall of our part is. But maybe we'll let it go slightly below that and say 1.8. We'll allow it to go down to 1.8. Then we have to decide on the steps that we're going to allow the system to vary this value by. So it's going to run a series of experiments or scenarios as they're listed at the top of the screen here. And each time it runs a scenario, it will slightly modify this value, and then it will monitor how that affects the overall mass of the part. So because we've only put one variable in the table here, this study will run relatively quickly. So I'm going to set this step size to something quite small. So let's see how many scenarios we get if we set it to 0.2. So I've entered 0.2 there. You actually have to click out of that box in order to get this value to update. So active scenarios 12. I think we may even reduce this down to 0.1 of a millimeter and then click out of the box again. So having had experience with these design studies before, I think 23 experiments or scenarios is acceptable in this case. So I'm happy with the setup of my variables. So the next area that we're going to look at is constraints, and in our case we need to tell the system that our goal for this study is to hit a range, an acceptable range of mass values. As I said before we began the study, our task in designing this part is to ensure that the mass is 82 grams plus or minus 0.2 grams. So our upper maximum limit is 82.2 and our lower maximum limit is 81.8. So we need to set those values within this next constraints area of the menu here. So if we have a look at the options here, the only option that we have is to add a sensor, and in this case we're monitoring the mass, so that's what we're looking for in the subsequent menus that pop up. You can see it's a very common value that gets monitored or optimized within these design studies, so it's the first option on the menu here. If we want to have a little bit of time to familiarize ourselves with some of the other options in here, we can monitor dimensions within the part or measurements between 2 points, for example. We can monitor the output of simulations, so if we've done a simulation where we got some stress values out of the simulation, we can monitor those stress values. So that can be quite useful when you're optimizing a highly functional part that has to have a certain upper stress limit that it can operate below. But as I've already said, the one that we're monitoring is to do with mass properties. What is it about the mass properties readout? Well, it's the actual mass that we need to monitor. Other things, if you remember back when we evaluated the mass, other values that we were told within that tool were the volume, the surface area, the centre of gravity in X, Y and Z axes. But again, we don't need any of these kind of further values. We're just monitoring the mass itself. And you can see what it currently is there. It's 90.28, which is too high for us. So mass properties, mass, and then click OK. So we can monitor the mass now. So what do we want to say about the mass? Well, we want the mass to be greater than our lower limit. So our lower limit is 81.8, which is just the value that we've been given minus 0.2. So this is the tolerance of mass that we're describing now. So then I'm going to add a second constraint. So the first one says that the mass is greater than this value. The second one is going to say the mass is less than our upper value. So our upper value will be 82.2. So we're looking for a mass figure somewhere within this window. So that is how you describe a mass tolerance to the system. You give it the lowest value that is acceptable, and you say I want my study to be greater than that, but it cannot go beyond this value. So we've fully described our tolerance, and then we can give the study an overall goal, which in our case it might be nice to try and use the minimum amount of molten material for this part, just in terms of cost. If you can design the part and it hits all the acceptable design constraints to do with mass, then it would be wise to try and use a minimal amount of material rather than paying for extra material. So we can give a kind of overall goal as well. So I'm going to add another mass sensor, and I'm just going to say within these values look to pick the solution which also minimizes the mass. So in that sense, tend towards the lower end of the range if possible. So that's kind of an overriding goal of the study. So when we've got the study set up like that, we can click on Run, and the system will calculate. So I may pause the video here until the system's done calculating. So here's the completed study. It didn't take very long to run there. It probably took about 30 to 40 seconds. So what have we been provided with when the study completes? Well, we get this table of outcomes from each scenario. So if we have a look at the table, if we have a look at the rows, the top row of the table here is telling us what the rib width was set for in each scenario. So you can see the rib widths being changed here at regular intervals. What are those intervals? They're the 0.1 millimeter that we gave the system as our step size here. So that is what we gave it in terms of the size between each adjustment that it makes. So you can see it changing the rib width. You can see the mass being monitored. So the mass is monitored for three different purposes. It's monitored firstly to try and hit a mass which is above 81.8. It's monitored a second time to try and hit a mass which is below 82.2. And then overall the system is just monitoring the mass just to try and minimize it as much as possible between these two values. So we have what the current setup was when we began the study. The rib was 4 millimeters thick. The initial agrees with that in this case. Then we have a series of experiments. Now these are all coloured in red, and that is because in this particular run our optimization was not successful. So you can see here it says optimization failed, and then if we kind of interrogate the table more, because we have so many scenarios that they actually go off the side of the screen here, so I'm kind of scrolling through them. So the fact that all of these are coloured in red means that they were all a failure. We did not reach a rib width which satisfies this mass goal. So what do we do now? Well, ultimately we will run a second design study, but we'll use the output of this unsuccessful one as our guide as to how to set up our second design study. So even within design studies, you the user can be involved to a certain extent and use the output of any unsuccessful studies as the input of any new studies that you create. So we're looking for a mass figure within this range. So what I'm doing here is I'm searching all the various scenarios and trying to find experiments or scenarios that were as close as possible to the figure that we're looking for. And I think, looking at this table, somewhere in this range is where our eventual rib width is going to be. And that is because we're looking for a figure which is just slightly above 81.8, and you can see when the rib width is set to 2.9, we're almost there. We're slightly below where we need to be. And then we're looking for a figure which is below 82.2. So again, when the rib width jumps up from 2.9 to 3, we just miss the window that we require. So our eventual solution will be somewhere between these two experiments or scenarios. So if we are now setting up a second design study, we will be wise to set the lower limit of the rib width to 2.9 and the upper limit of the rib width to 3. And then we can reduce the step size down significantly because we've tightened our search into a very specific window then. So 2.9 is the lower one, 3 is the upper one. So I can do that very easily. I go back to variable view, 2.9, 3, and then because we've reduced our window of dimensions that we are searching within so significantly, we can also reduce down our step size. So I'm going to go down by an order of magnitude. So I'd put an extra 0 after the decimal point there. So how many scenarios is that? It's still only 11 scenarios. So let's run that optimization now and see if that one's successful. Hopefully it will be. So here's the output of that optimization, and this one has been successful. You can see that in the readout here. 13 scenarios ran successfully. And the system's picked an optimal design for us here. So this is a very similar table, but some of the colorings have changed. So in our first table, because the entire design study was a failure, none of the scenarios satisfied our lower and upper limit for mass. This time, several scenarios have satisfied the lower and upper limit for mass. These ones here that are just left coloured in grey. So all of these ones have been successful. All of the red ones have still failed. But then of these successful ones, the system has given us the one with the lowest mass, because that's what we set as the goal. So the overall goal of our study was to try and minimise the mass within the successful candidates. And that is what the system has done here. So if we're happy with what we're seeing there, we can say to the system we want to accept this optimal setup. The way that we do that is just click the downwards arrow above optimal, and it will ensure that the model is adjusted to whatever the optimal value for our rib width is. So in our case it's 2.92. So if we click on the rib in the model and just check, it should have been adjusted to 2.92. Yeah, there it is. And then if we spot something that we're not happy with now and we've changed our minds, we can go back to the initial design if we want to. So we do the same thing. We click on the down arrow where it says initial, and then the model adjusts itself back to where it began. So you can pick any one of these scenarios in that same way. So in this case I'm going to accept the optimal. So I'll click on optimal again, and you can see the ribs reduced in size back to 2.92, the optimal value. So that's design studies. Uh, Sometimes you will hit the optimal value in the first design study, sometimes you will have to run multiple design studies, but the general method of working is even if the first one was unsuccessful, you can normally get some useful information about how you can set up the second or maybe third design study from that first unsuccessful one. So that's how you apply materials to a part, or apply a density essentially, how you evaluate the mass of a part manually in the first instance, and then how you use that ability to evaluate the mass as an input into a design study to optimize the design of the part itself.